Hey, Houston, we've had a problem here.
This is Houston. Say again, please.
Houston, we've had a problem.
Hey Houston, we have a problem. Today we want to talk about something we're going to introduce, a topic that has stymied physics students forever, and that's this topic. Free body diagrams. So it turns out that when we're talking about the forces that are acting on an object, there's a standard way that physicists draw these diagrams. Because you want to know what all the forces are with all the appropriate angles, and yeah, let's chat about a couple things. First of all, to make life simple, if you've got like a person, if I want to draw a free body diagram of myself, I'm standing on the floor. I mean, we could draw a stick figure of Mr. Bergman, or we could do whatever, or we've got a cat, or we've got a car, or we've got a train, or whatever. But physicists get lazy. All objects are a dot. So we don't try to draw a picture of a human. We just have a dot. So if we're to do what is the free body diagram of me standing on the floor, right? I am a dot. And I'm standing still. If I'm standing still, I draw an arrow away from me. This is the force of gravity. Now, I'm not moving, so there must be a force that's opposing my falling through the earth. And so, of course, that is the normal force. That is a free body diagram. Very simple free body diagram. Okay? Let's do a second free body diagram. But we're going to have somebody who is kicking a ball. So it's a soccer ball. So you got a soccer guy, and they're kicking a ball at 30 degrees off the turf on the soccer field. All right, so the ball is going to be represented as a dot because everything is a dot. Okay? And what's acting on the dot? Okay, there would be the force of gravity, always pushing down. You'll see that's always. I made it shorter, by the way, because like say if this was a 2 kilogram, let's say it's a 2 kilogram ball, it's going to, because I weigh a lot more than 2 kilograms. And of course, the normal force is also there. But there's a third force that I could draw at an angle, right? So if you're kicking the ball, and this would be the force of the kick, let's say. And then we might draw this here and write 30 degrees or whatever degrees that they're kicking at. That is a free body diagram. As a note, when you think about this, these two will cancel out, but the ball will accelerate off into the right and cause it to accelerate and move, et cetera, et cetera. So you can draw them in lots of different ways at different angles, etc. And if you want to find, ultimately you want to do is figure out what's the net force. So, or we say the sum, the big funky E is the sum of the forces. And this one is 0 because Fg, oftentimes they say Fg equals Fn, but that's not 100% true. It's just Fg is negative and Fn is positive, and they're the same number, so they cancel out. In this case, that would be true here. This is the normal force. The normal force and the gravitational force cancel off, but now we do have a net force of F, kick, and maybe I say this is, they kick it with 30 newtons of force or something like that, equals 30 newtons at 30 degrees, and we probably say above the horizon. Now, what I'm trying to do is just show you how we draw these. Let's do something maybe more complex. One more. Let's say that you're on a ski hill. Okay. Or you've got a ramp, and it's 25 degrees. I don't know. And then we're going to put a dot right here, and always we've got gravity going down. And remember we talked about the normal force is actually perpendicular to the surface. So this is the normal force, but you've also got another force going up this ramp, and that is the force of friction pushing it down. So these are the three forces that you would have on a box or a car or whatever on some kind of a ramp, and this is going to be the free body diagram. And we'll get to more complex ones where you have all kinds of other things. You could have somebody who's pushing this cart, box, ball, whatever it is, down the hill, and so you might have another force that's like this, and then we'll have to overcome the force of friction. So if the force of friction is 10 newtons, and I push with 20 newtons down the ramp, then the net force down the ramp is, 20 minus 10 or 10 newtons or something like that. And then there'll be something to do with this normal force. We'll talk about later how it's related to the frictional force. But ultimately, you got a dot, and then you draw arrows. Notice all the arrows come out of the circle. You don't have arrows. So when I said on this one here, when I said you're going to push that object, I don't draw an arrow like this. No. You draw arrows that go away from the circle. So you're always, even though it's a push or a pull, we always draw them as pulls. This is pulling it up, this is pulling it that way, and it just makes it easy. And you're just going to get a lot of practice in class learning how to draw free body diagrams, and we're going to do this over and over and over again, and they'll get increasingly complex. This is just the brief introduction to free body diagrams. Houston, we don't have a problem. We'll see you in class.